Welcome to another episode of Automat Devlog. This one is going to be slightly Linux specific. I'm going to tell you about static and dynamic linking. First, I will show you some arguments for and against dynamic linking, give you some advice, and then show you how my debugging workflow worked for this particular issue that I had here. I will try to end on a positive note. It's not a very optimistic area, but we kind of have to be if we want to make it work. So dynamic linking. Dynamic linking in general is a practice of shipping incomplete applications that can then pull in the relevant missing pieces from the target operating systems. There are some issues about this thing. One of the issues is that those dynamic libraries, they really depend on the type of the system that you build it on. If you build it on one distribution, it usually will not work on another or even a previous version of the same distribution. If the libraries that you are using are lost for some reason, this happens. It becomes very hard to run your library. You need to take care to properly ship those libraries, or at least think about how you will ship them. You can either embed those dynamic libraries within the installer, or you can download them dynamically from your server, from operating system servers, or you can just ask the user to install those libraries for you somehow. But the distribution is a hassle if you ship the dynamically separately. Stability is an issue. Recently we had a very fast pace of development in AI. So the AI-related libraries, they very quickly iterated on their API. And even though they used a versioning scheme called semantic versioning, it still failed because the authors of those libraries, they quite often simply forgot to properly annotate all of the changes that they made, and the result was just a very painful experience of using, of building anything AI related on any computer. Then dynamic libraries are also not great for performance because they have to be linked, all of the calls, they have to go through a PLT or GOT, like indirect sections. And even if they don't, they still have to be linked at runtime by the runtime linker. Big software, I mean software that uses tens of libraries, often runs into an issue of daemon dependencies, where different libraries that they use, they have a common shared dependency, which they require at a different version, so doesn't work. When this happens, you have to either downgrade one of the libraries or fix one of the libraries to use the more recent version of the dependency. It's a big issue and it takes a lot of time to fix all of those things. In the end, when a user actually tries to use a dynamically linked program, typically the app just works on one system. And when it doesn't, you get totally esoteric error messages, like it's not an executable. So an error message, something like that, happens when you don't have the right runtime linker, like LDSO. And when the libraries are missing, you get a, I would say, nicer error message, but when you look at this error message, try to think not as yourself, not as a programmer, but as a user of an application. Think about a kid or an older person looking at this and seeing an error message saying that error while loading shared libraries, and then a sequence of bizarre characters, cannot open shared object file. This is totally esoteric language. Nobody is going to understand this stuff. Dynamic libraries are not great. They result in pretty bad user experience and pretty fragile software. So what's good about them? There are a couple arguments for those libraries. First, they are more efficient when it comes to memory usage. It may seem like a very weak argument nowadays, but historically, if you go back 30 years or 20 years even, you will see that there was still a debate about how do we want to ship software. And memory consumption as crazy as it sounds, was the major argument for dynamic libraries. This is one of the reasons why Linux is so memory efficient nowadays. You can have a 1 GB system and it's perfectly fine for a modern system. This is because Linux mostly uses those dynamic libraries. And it was historically the major argument. They can be also good for performance. I said they can be bad for performance because of their linking overhead, but the native libraries can also be built differently. So this is mostly a theoretical argument, because in practice, I don't think I have ever seen this. In theory, you could have a faster build of FFmpeg or faster build of PyTorch on your machine, but in practice nobody does this. So there is that. There is also a security argument. So if there is a security flaw in one of the dynamic libraries, theoretically and in practice, it can be updated more quickly and pushed to all of the users more quickly, and it results in all of the applications that had this security flaw being patched. It's a really nice thing. It's a really convenient way to patch apps. But it's not a killer argument in the sense that you can still patch those applications by just rebuilding their statically built versions. Performance is also not a really kind of killer argument because, well, we could still use static linking and that would still work. Same for memory consumption, and none of those arguments against dynamically linked libraries are also super strong, because yeah, they are terrible for portability, maintenance, distribution, stability, performance, large software, but they still work in all of those cases. They introduce a lot of pain, but they still work. There are 3 arguments for dynamically libraries, which are those killer arguments. There is just no way around dynamically linked libraries if you want to have those things. So first are plugins. If you have a plugin and you don't have a well-defined protocol of talking with this plugin, for instance, if it was running in a separate process, then it has to run in your own process, then it has to be a dynamically linked library. Then some system interfaces, they are kind of like that, they don't have a well-defined protocols. A few common ones are graphics, especially the 3D graphics, audio, and input handling. When we are writing applications, when we write them today, we want them to still work 10 years from now on future hardware. So the only way to make this happen right now is to rely on dynamic libraries. They expose foundational interfaces for applications that allow them to work long time after they have been compiled. Then there are also some libraries which haven't been designed carefully. So whenever a library contains some global state, this is when you cannot really link it statically anymore, because 2 different components of your system, when they link this library statically, when they want to use different versions of your library, it just results in big issues. Unfortunately, because of the POSIX standard, this is kind of how libc and memory allocation works. This is how threads work, and this is how some interfaces on operating systems like the PAM authentication and DNS name resolution also has some issues related to plugins that can be loaded for DNS name resolution. Dynamically linked libraries may not be the best always, but for some things they are necessary. So my advice in this area, I'm not a huge authority, but my advice still is to only use them when they are necessary. But otherwise to try to actively work towards switching this into a static version. The reason for this is the better experience for the end user. This is the end goal. This is everything else doesn't matter. because it has to be easy, robust, it cannot crash. So I also mentioned I will give you my debugging workflow that I use when I have to fight against static and dynamic linking issues. So this is something that happened like Friday. So we realized that we have to translate key codes into UTF-8 character sequences. This is a complex problem because different machines do this differently. If you go to some Asian country, they use completely different alphabets. The translation from key code to UTF-8 uses rather complex infrastructure of kind of applications that do this translation. It's not an easy task to do this properly, so we had to use a library. So we pulled in libxkb common, which can be embedded as a static library, but quickly it turned out that this library doesn't really want to properly talk over our XCB connection to the X11 server. Short while later, we realized that we are using shared libxcb and we have to switch to a statically compiled one. So, after properly linking in a shared version of libxcb, we are doing this using flags like this one. Then we can actually embed libxcb, but in a way that it can still be used. So it actually tricks the linker into using our embedded libxcb. So we are re-exporting libxcb, embedding it statically, but also telling the linker, hey, it's built in, you don't have to load anything. We realized that it was the problem because we had proper logging set up. This is the first step of the debugging adventure. Even if later on you switch to a better tools, you always start with printf. Then I switched to GDB, and GDB has those nice options where I could enable debugging of LDSO. If you run LDSO, you will see that it explains some flags that you can introduce. LD-debug. That will allow you to see what's happening in the linker. And this approach, it shown us that even though we are starting with our built-in libxcb, the moment we load Vulkan, it pulls in an external version of libxcb. So we are effectively loading the library twice. But still, the LD-debug showed us that even though it loads an external libxcb, all of the symbols are actually resolved to our correct embedded version of libxcb. So in this case, we actually had this library loaded twice. One version loaded from user lib64 and another version loaded inside our binary. It's not listed here. So this command is very useful. This is a GDB command that prints all of the libraries which are loaded. And by stepping through and invoking this, you can see what's kind of happening in the linker. So we knew that the issue was still happening. The next step was to run strace. So strace is a program that can capture system calls from one application into a text file, essentially. So this is what I did. I executed Automat dynamically and statically to produce those strace files. And here I could compare what were the differences between them. And the differences were tiny, and they were exactly around loading those libxcb libraries. See, the dynamic version loads them earlier, and the static version, it still loads them, it just does it a little bit later. Yep, here. I went through those two files, basically line by line, looking for differences, and nothing was apparent except that we have a connection to the X11 server where we are sending messages. So we have a lot of these write v and receive message. They are just sent back and forth all the time. And strace doesn't really present them in a easily readable way. So the next step was to actually capture those messages. And there is a trick to do this. using Wireshark. So we are lucky that we are using X11 because X11 can run over the network. So I created some fake network connection, local network connection to my local X11 server, where the application could talk through the localhost interface. Then I executed Wireshark and captured this traffic. And Wireshark has this nice thing called protocol dissectors, and it has one for X11. So if you can capture X11 trace, you can analyze this using Wireshark. So I did capture 2 traces, one for the dynamic version of our app and one for the static. And then I went line by line looking for differences between them. And I found some. The differences were very subtle. It was about the data that the NVIDIA driver exchanges when it's negotiating kind of connection to the native driver. So it was sending slightly different keys or identifiers. They were like 16-byte hexadecimal semi-random strings. Comparison of those traces actually told us what was the root cause. And the root cause was that the Vulkan driver that NVIDIA ships does some crazy stuff. So one very strong telltale sign of crazy things happening is that we have a lot of proc self-maps parsing. This should never be the case. No application should need to parse its own proc self-maps most of the time, unless it's doing some crazy hacks. So this is what NVIDIA driver is clearly doing here. Because of that, it seems like it is mismanaging the XCB connection. It is introducing some global state, essentially, to the XCB library. I'm not sure exactly what this global state is, because this library is closed source. It's a proprietary driver blob, but there is some global state there that prevents us from having a nested version of libxcb. So plans for Automat are as follows. 1. There is actually a way to make a static library that still loads dynamic libraries. There is a nice presentation by Andrew Kelly. He is the author of the Zig language, where he shows a trick that can be used to achieve that. You can essentially just remove the interpreter annotation from your library and it suddenly becomes a static library. So we can do this, it can work. This trick allows us to still use the C library of the target operating system, so we can still use DLOP and DLSim for everything. So we can still use dynamic linking for most libraries and static linking wherever we can. There is hope that we can produce a single binary that will just work across all Linux operating systems. And this is the positive note for the devlog I would like to end with. See you in the next devlog episode.